In this video, I want to talk about heteroskedasticity. But let's first start with the opposite situation, which is homoscedasticity. So homoscedasticity means that along the regression line, so for different values of y and for different values of x, the variance of the error term is constant. So whether we have a low value of x or a high value of x, a low value of y or a high value of y, if we look at the associated predicted value, the associated regression line, then the variance of the error term around that line should be constant. And so this is something we say about the model. It's not about the residuals in our sample, it's about the model in the population. So we are assuming homoscedasticity. We are assuming when we run our regression that the variance is constant. So heteroskedasticity is the opposite situation. It's a situation where along the regression line the variance differs, where at some points along the regression line the errors are very small, and at some other points along the regression line the variance of the error term is high. So any regression where the disturbances or the error is varies, is not constant across observations, is a heteroskedastic model. And with heteroskedasticity, the estimate of beta hat is still okay. So the unbiasedness of the beta hat, the OLS estimator of beta, is still intact, but it is not longer blue or asymptotically efficient. So that means that among the linear unbiased estimators, OLS might not be the most efficient anymore. Right? That is what blue meant. Blue means that among the unbiased linear estimators, OLS is the most efficient, has the smallest sampling variance, the smallest standard errors. So with heteroskedasticity, this is not true anymore. So there might be other linear estimators that have a smaller variance that are more efficient. Yeah, so they have a smaller sampling distribution or a smaller sampling distribution as the sample increases. Now there are many potential causes of heteroskedasticity. If I look at firms making profits, the variation in profits for large firms will be much larger than the variation in profits for small firms. If I look at the behavioral variables across different groups, one kind of groups might show much greater variation in behavior than another group. If I look at data over time, maybe there's a learning effect and there are greater shocks at the beginning and then smaller shocks at the end. Or maybe a big shock leads to a chain of shocks. Yeah? So that a shock at one time can reverberate in for a while and lead to additional shocks for a while. So there's all kinds of reasons why heteroskedasticity might occur. It might also occur because the function specification is just wrong, the shape is wrong. If we have a quadratic relationship but we try to estimate a linear relationship instead, then for some parts of the line the variance will be much higher than at other points of the line. So if the assumption of a linear relationship is not a good assumption, you're likely to get heteroskedasticity. So there are many potential causes of heteroskedasticity. We will see in a bit that this also makes it harder to test for heteroskedasticity because there are so many ways in which it can go wrong that you don't really know against what you're testing. And also solutions can vary radically because there are so many different causes. And so if OLS is not blue and is not asymptotically efficient, it means that other estimators might exist that are better than OLS at estimating this data. Yeah, that might have smaller sampling variances. That might come up with the same or similar beta estimates, but that give smaller standard errors. Or there might be estimators that are similarly consistent, but that are collapse faster in the sense, meaning that you need a smaller sample size to get good estimates. It might converge quicker with a smaller increase in the sample size to a good estimate. And finally, if we do not have an efficient good estimator, we also need to put question marks around the standard errors we have. So the unbiasedness of the estimates of the beta coefficients remains, so we can trust our estimates for beta, but the estimate for the variance covariance matrix breaks down, and we cannot trust the t-test or the standard errors that we obtain. So when the data is heteroskedastic, it becomes problematic to look at the significance test on the t-test for each of the coefficients. Right? We looked at this matrix, the expected value of epsilon times epsilon prime. So this is the expected value of the variance covariance matrix of the errors. And you might remember that when we derived the estimator for the variance covariance matrix of beta hat, we used the expected value of the variance covariance matrix of the errors, which is this n by n matrix which zeroes off the diagonal and this constant variance on the diagonal. So a heteroskedastic model means that this constant variance across the diagonal does not apply, and this variance changes for each of the observations. And that means that we cannot just say sigma squared times I as a shortcut for this expected value. And that means that in the next slide, when we derive the variance of beta hat OLS, we have this longer equation that we obtain, and we cannot simplify beyond that. So we can say that there is a variance covariance matrix of the errors called omega, but we need to now do something with that. Rather than just assume that it is sigma squared times I, which is saying there is no autocorrelation and no heteroskedasticity, and then we can simplify this equation, we need to do something else to move beyond this step. So bottom line, if you have a heteroskedastic data, which can be caused by many different causes, can easily happen, your beta estimates are fine, but you cannot trust your t-tests. And to address it means that we need an alternative estimator for our standard errors.